Hi everyone, I am Rami Razi Perchikolai and this is a joint work with my colleagues at Rakuten. In this presentation, I want to talk about learning the inputs and how it can improve the results of recommendation systems and neural collaborative filtering. The goal is to predict the ratings of the users on items. Let's say we have m users and n items and we have access to the rating matrix, which is m by n. Some of the ratings are known, and in most applications 95% to 99% of the ratings are unknown, and the goal is to learn a recommender system that predicts the unknown ratings. Neural collaborative filtering is a very recent approach. It takes user representation and item representation, concatenates them, and trains an MLP to predict the rating. The focus of our work is on learning user and item presentations, and I'm only going to talk about user representation because item presentation can be achieved in the same way. Most state-of-the-art methods use user interaction vector as the input. They train an MLP and they generate the user representation. Let's see more detail about how it works. First, what's an interaction vector? It's a row in a rating matrix R. In other words, for each user, the interaction vector contains the rating of that user on all the items, and it's 95% to 99% sparse. What does MLP-G or the user MLP learn from this interaction vector? We looked at the first layer of this MLP, and we show it here, when we assume there is no activation function for now. We notice that the weight matrix of this layer is n by d, and n is number of items. So for each item, there is a d-dimensional vector inside the first layer of the user MLP. We call this implicit item embedding. The output of this layer is the weighted sum of some of those embeddings. Which ones? The ones that the user rated. And what are the weights? They are fixed to the ratings. Here is a summary of what I said. First, the weights of the first layer of the user MLP is an implicit item embedding. Second, the user initial representation is the weighted sum of the item embeddings. Which ones? The ones that the user rated. And finally, the weights in the weighted sum are fixed to the ratings. What we are proposing is that we can initialize the weights or the input from the rating or interaction vector, but we can learn it. And by learning that, we can learn better representations. Here is the objective function of the previous works. They learn the parameters of three MLPs. One that maps the representations to the rating. The other ones are the ones that learn the user and item presentations. In our case, we introduce two new variables, user input vectors U and item input vectors V. And in addition to the MLP parameters, we learn U and V. They only appear in, as you can see, they only appear in the input layer. In our work, we show that first, by doing alternating optimization, we can and initializing the input vectors from ratings, we achieve better training error. And second, we show that at the test time, our method uses the same number of parameters as the previous works. So our model complexity is the same as the previous work. We achieve better training error, so we have a smaller generalization bound. We compare our method with different methods on 4 different datasets. ML100K is the smallest one, Ichiba is the largest one. We report RMSE, the smaller the better, and precision, the higher the better. We compared our learning the input strategy with fixing the input of the previous works. So we report results on Ichiba and ML1M. Let's focus on Ichiba. As you can see, for the fixed input, we change the number of parameters such that they can have number of network parameters of 62 million to 620 million, but they don't have any input parameters. For us, we use 62 million parameters and 2 million input parameters. You can see that our approach achieves better results than both of these two structures. So essentially, it's not about increasing the number of parameters. It's about learning better parameters and learning the inputs to learn better representations. The same conclusion holds for movie-lens 1M dataset. Here we compared our method with many state-of-the-art and baseline methods, and we achieved better results, lower RMSE and better precision. The conclusion is that the non-zero elements of the interaction vector are the weights in combining the embeddings and computing the weighted embedding, and learning them leads to learning better representation. Thank you.